Today I'm going to discuss and find in what sense angular momentum is conserved for a particle moving under the influence of a centripetal force. So let's start with scenario 0 or scenario 1, where the centripetal force or central force equals 0. So in that case, let's have the center be the origin of a Cartesian coordinate plane. There'd just be a particle moving at a constant velocity since the central force equals 0. And let's denote this distance, r0, from here to here. Now, is the standard definition of like the high school definition of angular momentum, is m or v conserved? Well, we can find that out. Let's say at some time the particle is here, and at another time the particle is here. So, and let's denote this distance from here to here as r, and this distance from here to here would still remain r0. So v0 remains the same, or velocity remains the same, radius changes, and mass remains the same. So the angular momentum value of this particle right here, it would be m times r times v0. And the angular momentum value of the particle over here would be m r0 v0. But these r's are different. We get this, r equal r0, which is not true. So hence, m or v is not conserved for any particle under the influence of a central force. It is only conserved in a really special case, namely circular motion. But angular momentum is still conserved for a particle moving in this type of motion in a certain sense. And that certain sense is that the velocity component perpendicular to the radius value. Velocity component perpendicular to the radius value times the radius times the mass remains constant. So this component of the velocity times this radius times the mass remains constant. And I'm going to prove that to you right now. So this component, all right. So we know this is, let's call it v perpendicular. This is the velocity component of v0 that we're looking for. v0 is the actual velocity, and this is the other component of v0 that we're not too worried about. Let's make this angle theta. Hence, if this is a right angle, sine theta would equal, well, opposite v perpendicular over v0. And hence v perpendicular would equal v0 sine theta. So let's draw it over here. And this would be angle theta. Oh yeah, my lines are not perfectly drawn, but oh yeah, this should be a right angle. So this is theta. This would also be theta. And hence this would also be theta. You can prove this using geometry. If this angle is theta, and this is a right angle, and this is a right angle, then this must be theta, and this must be theta. But if this is also theta, then sine theta also equals r0 over r, or opposite over hypotenuse. So sine theta also equals r0 over r. Now we can prove that v perpendicular rm is constant. So if v perpendicular just equals v0 sine theta, then this just equals m r v0 sine theta. And if sine theta also equals r0 over r, then v perpendicular times r times n just equals m v0 times r times r0 over r. And hence this just equals m v0 r0 if we cancel out the r's. But look, r0 remains constant because it's the distance of the velocity line to the x-axis. v0 also remains constant, and m remains constant. Hence, v perpendicular times m is constant, and angular momentum is constant or our special definition of angular momentum is constant for something under a central force of 0. But what happens if there's like some sort of force or impulse that's directed toward the center? What if the central force is non-zero? So we'd have something looking like this. And all of a sudden it would be hit by an impulse. In my previous video, I found that if this is RF, which is perpendicular to the velocity line and touching the center, this distance from here to here is RF, and this is R naught, and it's initially moving at some speed V naught, and it ends with some speed VF. V naught, R naught equal VF, RF. I proved this in my proof of Kepler's second law, so it's the second latest video I did. Alright, so we know this to be true. So let's take this line, let's just rotate our thing here and make a new graph. So it looks something like this. There'd be a velocity line going here, VF, and this is RF. Well, we know for straight lines, angular momentum is conserved, or mv perpendicular times r is conserved. Namely, mv perpendicular r would equal mvf rf. Because this scenario, where this is like some r, looks exactly similar as this scenario. So we can just generalize that. If mv perpendicular times r times m equal mv naught r naught, and we just change the constant velocity in the distance of the velocity line to the origin, this must equal this in this case too. But in our previous video, we proved that v naught r naught equal vf rf, then hence mv perpendicular for the second line, we're only considering this line here, equals mvf rf, and hence it also equals mv naught r naught, and hence the angular momentum value of this line equals the angular momentum value of that line too. So these two are equal because as I've shown here, and v naught r naught equal vf rf. And we can also think of this as like multiple impulses, or so many impulses that it starts to look like an ellipse, where this is v naught, this is v1, this is v2, this is v3, this is v4, this is v5, this is v6, and it has a height of to some point, or perpendicular height to some point of h naught, and this would have h1, and this would have h2, and v naught h naught would equal v1, or I should use r actually. V naught r naught would equal v1 r1 would equal v2 r2, and hence mv perpendicular times r would equal, well, at this point it would equal v naught r naught, but v naught r naught also equals v1 r1. So at this point, the angular momentum value would also be mv1 r1, which also equals mv naught r naught, and hence mv perpendicular times r is conserved. Now, is mvr conserved? I'm going to prove that's not the case. So let's take an ellipse. And let's make the sun at the center, or at the origin, which is this is the focus. Let's make this distance r naught, and it's initially moving at a speed of v naught. Let's say the planet is here. It's at a distance r from the center, and it's moving in this direction, and it has velocity v. So we know mv perpendicular times r is conserved. So this component of this actual velocity right here would be conserved, and hence mv v cos theta times r is conserved, because this component right here is just v cos theta. So if mv cos theta times r is conserved, and this would equal, yeah, if mv cos theta times r is conserved, is mvr conserved? Well, no, it's not conserved, because it simply isn't, because only mv cos theta times r is conserved. That means mvr is not conserved. Or we can, yeah. However, the angular momentum, or MVR, of this value here would actually equal the MVR over here, because both have a cos theta of 0. So hence it would just equal, or only for these 2 points, it would equal exactly MVR, because theta is 0. And hence, if mv perpendicular times r equals exactly just mvr, then mv perpendicular times r would equal mv naught r naught. And if it has a speed of, let's say, vf and a radius of rf, this would also equal mvf rf. And these are the only 2 points where the actual value of MVR equals both the angular momentum value, and it also equals each other. All right, that's this tangent video that nobody asked for, and thank you. Bye.